In 1977, humanity launched two machines with no faces, no emotions, and no promise of survival. Their mission was supposed to last just a few years. Instead, nearly half a century later, they are still talking to us, from a place no human-made object had ever reached before. Far beyond planets. Beyond the sun's reach. Beyond the comfort of certainty. Voyager 1 did not just travel farther than anything we have ever built. It crossed boundaries we did not even fully understand when we sent it. Boundaries of distance, of technology, of time itself. Along the way, it revealed worlds that shattered our expectations, rewrote textbooks, and forced us to rethink what the solar system really is. And now, at the very edge of the sun's influence, Voyager 1 is detecting something even more unsettling. Not a dramatic explosion. Not a clear line in space. But a transition, a whisper that tells us our models were too simple, our assumptions too neat, and our place far more fragile than we like to admit. This is not just the story of what Voyager 1 found out there. It is the story of why it was able to find anything at all. One of the most remarkable things about Voyager 1 is not where it is, but the simple fact that it is still alive. Designed in the early 1970s with computing power that seems laughable today, Voyager was never meant to operate for decades. Yet it continues to function in the extreme cold and relentless radiation of deep space. The secret lies in choices that seemed excessive at the time. Voyager does not rely on solar panels because engineers knew sunlight would become useless far from the sun. Instead, it carries radioisotope thermoelectric generators, systems that convert the steady heat from decaying plutonium-238 into electricity. The principle is almost primitive in its simplicity. As long as there is heat, there is power. And although that power decreases slowly year by year, that decline was always part of the plan. Every critical system was built with redundancy. Instruments duplicated. Backup pathways ready to take over. Components that could be shut down to conserve energy. Multiple thrusters to maintain orientation. Because once Voyager left Earth, there would be no repairs, no upgrades, no second chances. Every problem would have to be solved through logic alone, from billions of kilometers away, with commands that take nearly a full day to arrive and another full day to confirm whether they worked. Voyager 1 is not still operating by accident. It is alive because it was built by people who assumed everything would eventually go wrong and prepared for it anyway. What makes Voyager's survival truly epic is the mismatch between human time and cosmic time. Voyager 2 launched first in August 1977. Voyager 1 followed weeks later in September. But Voyager 1 took a faster, more direct path, overtaking its twin and becoming the first to race toward the outer edge of the solar system. Two machines born together, separated by destiny. The mission was never designed for longevity. Engineers built Voyager for a short journey, hoping that if everything went perfectly, it might last a little longer. They gambled on the future, and against all odds, they won. Decades passed. Generations of scientists retired. Technology on Earth transformed completely. Yet Voyager 1 kept going, quietly accumulating radiation damage, losing power bit by bit, and still sending data back as a faint whisper across billions of kilometers. Every successful command sent to Voyager today is an act of patience and trust. A move in a cosmic chess game where one mistake could mean permanent silence. And yet, despite its age, despite its limitations, Voyager 1 continues to report measurements from a region no one had ever directly explored before. It is a machine from the past, surviving in the future, operating on a timescale no human life can match. And that endurance is what made everything else possible. Without it, the discoveries at the edge of the solar system would have remained forever out of reach. What allowed Voyager 1 to reach the edge of the solar system was not just engineering brilliance, but timing so rare it borders on the unbelievable. In the late 1970s, the outer planets aligned in a configuration that occurs roughly once every 176 years. Jupiter, Saturn, Uranus, and Neptune formed a celestial corridor, a gravitational pathway that could send a spacecraft across the solar system in a fraction of the usual time and energy. This alignment became known as the Grand Tour. Without it, Voyager's journey would have been impossible. Reaching all the outer planets individually would have demanded far more fuel than any rocket could carry. The opportunity was fleeting. Miss it, and humanity would have waited nearly 2 centuries. Without it, Voyager's journey would have been impossible. Reaching all the outer planets individually would have demanded far more fuel than any rocket could carry. The opportunity was fleeting. Miss it, and humanity would have waited nearly 2 centuries for another chance. Scientists and engineers understood the stakes. This was not a routine launch window. It was a now or never moment written into the mechanics of the solar system itself. The decision to launch Voyager was therefore not just scientific ambition. It was audacity. Humanity chose to gamble on a rare cosmic arrangement, trusting that precise calculations and flawless execution could turn planetary gravity into a vehicle. The Grand Tour was not created by humans. It was discovered. And Voyager 1 was built to take advantage of it before the window closed forever. The true genius of the Grand Tour lay in the gravitational assist, a maneuver almost like an elegant cosmic theft. As Voyager approached a planet, it fell into its gravitational well, accelerating dramatically. Then, at precisely the right angle, it slingshot around the planet and escaped, carrying away a small fraction of that planet's orbital energy. The planet barely noticed the loss. Voyager gained everything. Jupiter was the first accomplice. Its enormous gravity bent Voyager's path and hurled it forward at incredible speed. Saturn took its turn next, reshaping the trajectory again, flinging the spacecraft upward and out of the plane of the planets. Each encounter was irreversible. A single miscalculation would have sent the spacecraft spiraling into deep space or directly into a planet, ending the mission instantly. This sequence transformed Voyager from a modest spacecraft into the fastest human-made object ever launched. It did not carry the fuel to travel that far on its own. It borrowed motion from worlds billions of times more massive than itself. This was not brute force. It was finesse. A precise understanding of celestial mechanics turned the solar system into a launch system far more powerful than any rocket. By the time Voyager 1 left Saturn behind, it was no longer just exploring planets. It was on an escape trajectory. The Grand Tour had done its job. Voyager was free to head toward the outer darkness, propelled not by engines, but by a once-in-a-generation alignment that humanity was clever enough to use before it disappeared. Before Voyager, the outer solar system was imagined as a quiet, frozen place, inactive moons circling distant giants. That assumption collapsed almost immediately. As Voyager flew past Jupiter, its instruments revealed something no one had predicted. Io, one of Jupiter's moons, was not geologically dead. It was violently alive. Voyager detected active volcanism, with towering plumes erupting hundreds of kilometers above the surface, reshaping the moon in real time. This single observation shattered the belief that small moons lose their internal energy quickly and go silent. At the same time, Europa emerged as something equally unsettling, but far more subtle. Its surface appeared smooth, bright, and fractured, marked by long cracks suggesting movement beneath the ice. Voyager did not see an ocean directly, but the patterns were impossible to ignore. They strongly hinted at a liquid layer below the frozen crust, introducing for the first time the idea that an icy moon, far from the Sun, could host vast amounts of liquid water. These discoveries forced scientists to rethink planetary heating, tidal forces, and the potential for habitable environments beyond Earth. The solar system was no longer a collection of dead rocks orbiting distant giants. It was a dynamic system where energy, motion, and hidden oceans could exist in places no one had ever considered. Voyager didn't just add data. It destroyed assumptions. As Voyager continued outward, each planet added another fracture to our understanding. Saturn's rings, once thought to be smooth and uniform, were revealed as extraordinarily complex structures made of countless thin ringlets, sculpted by small shepherd moons. Voyager detected unexpected features within them, including strange spoke-like patterns that didn't behave like solid matter or gas, a reminder that even familiar beauty can hide unresolved physics. Uranus delivered a shock of a different kind. Voyager discovered its magnetic field was wildly tilted and offset from the planet's center, creating chaotic interactions with the solar wind. The planet itself appeared to be rotating on its side in a way that suggested a violent past. Neptune, far from being calm and frozen, revealed winds faster than any recorded elsewhere in the solar system, and massive storms tearing through its atmosphere. By the time Voyager completed its planetary encounters, the solar system no longer felt predictable or orderly. Every world had refused to behave according to expectations. Each flyby forced scientists to revise models that had seemed solid just years earlier. Voyager transformed the outer planets from distant points of light into complex, active worlds, proving that even in our own cosmic neighborhood, nature is far stranger and more energetic than we ever imagined. Leaving the solar system did not happen with a dramatic sign or a visible wall. What Voyager 1 revealed was something far messier.